All right, so we looked at the free particle states, but in general, again, let me just write this for completeness. We have I bar del psi del t is equal to h psi type of solution, the Schrödinger equation. Psi we separated into two parts, a time-dependent part and a part that depends on space. So this is the e of x and e to the minus I e t or h bar type of solution, which means that the general form of the solution is the linear combination of functions of this form. Okay, and then let's, so the idea again is that someone has given us psi x at 0 is given by a, when we are posed with the problem, and then we are going to expand this, okay, using these eigenfunctions ue of x. How did we do this? Okay, we use the orthogonality of these ue's, because if they are discrete, we know that these ue star of x, ue of x dx is in the form of delta e prime, okay, e prime. I'm still discussing a discrete case. So that means that I can determine these CEs by using orthogonality. I just multiply ue star of x psi x 0 dx. Okay, the integrals are minus infinity to infinity. And once I get these CEs, I just put them into my equation so that psi of x and t is equal to sum e ce u e x e to the minus I e t over h bar. Okay, so what happens if we have not discrete states, but continuum states? How can I, how do these things change? Well, things just go to integrals. So the, in the case of the free particle, okay, so obviously I forgot to write that this ue of x is just, let me squeeze it here, is just the eigenfunctions of the Hamiltonian operator. So in the case of the free particle, my h is just h bar squared k squared over 2m, and well, I'm sorry, h bar squared p squared over 2m, with p the momentum operator. And what I end up getting, okay, so h ue equals e ue implies that this ue has the form e to the I k x, where k and e are related by h bar squared k squared over 2m is equal to e. Okay, so, and then we see that with plus for each energy there's a plus k and a minus k. So in order to remove the ambiguity, we label these functions with the index k. Okay, so we can differentiate between positive k and negative k. In the case of E, you don't have that distinction. All right, so having said that, if now someone gives me a psi x0, I need to expand it in terms of these functions, but now these functions form a continuum. So I define my expansion in such a way that there's a factor 1 over square root of 2 pi in front. Okay, and then I have this, instead of C, E, I have these expansion coefficients gk, and I multiply this by e to ikx dk, minus infinity to infinity. And since this is the Fourier transform relationship, I can easily find what g of k is. Basically, it's the same sort of thing that we are doing here, except that now the eigenfunctions are these e to the ikx's. So I'm going to get this g of k equal to 1 over square root of 2 pi minus infinity to infinity psi x0 e to the minus ikx, okay, dk. So the complex conjugate of the function comes in as e to the minus kx and so on. Okay, so this is more or less where we were last time. Okay. So what I want to do this hour is just to work on an example, and it will be a useful example. It will be the example of a Gaussian wave packet. Okay, so as my initial wave function psi x0, I am going to take my favorite wave function e to the minus x over x0 squared. Okay. We will need the integral several times, so let me put it over here. Minus infinity to infinity e to the minus some alpha x squared dx is equal to square root of pi over alpha. So if I want to normalize this, I'm going to get two of these things, and therefore a is going to be equal to what? Okay, pi over two of these things, so it's going to be 2 over x0 squared, okay, square root, but then I have another square root, so it's minus 1 over 4. So I end up with 2 over pi to the power 1 over 4, 1 over square root of x0. Check my algebra, please. Okay, so if I choose A like this, then this psi x0 is properly normalized. Yes?
For the integration of the gk, isn't it for the...
Yes, I have put in the wrong variable here, thank you. Okay, so I integrate this over dx. So I'm just doing this integral here. Okay. All right, let's see what the g of k corresponding to this function is going to be. Okay, so g of k is going to be 1 over square root of 2 pi. A is still there. And integral minus infinity to infinity. Okay, e to the minus x over x0 squared minus I kx dx, right? That's one. All right, so I have to evaluate this integral, and whenever you have a Gaussian integral like this, the trick is to complete the square of the exponential so that you are going to get a Gaussian which has been shifted by a certain amount plus another term. Okay, so what I'm going to do is I'm going to write this as a over square root of 2 pi integral minus infinity to infinity e to the, okay, x plus or minus something squared. But I am going to adjust it so that it gives me these terms plus an additional term which I have to remove, which I have to subtract out. Okay? So what I want to do is I have coefficient of 1 over x0 squared here. So I'll put that down, minus 1 over x0 squared. Okay, x plus or minus something squared. And when I square this, you see I'm going to get x squared over x0 squared. So first term is okay. But I also want to get this term. So how do I get that? Well, there's a minus sign here already, so it's going to come in with a plus sign, right? So, okay, ik over 2 is nice, but I also have this which I don't want, okay? x0 squared, right? So now, if I square this, I get the first term. That's good. I get the second term. That's good. But I also get another term, which is bad. It's not good. Okay, so I have to remove that. Okay, so let's just expand to see what this is. This is 1 over x0 squared, x squared plus I k x0 squared. Okay, so that's okay. The next term is going to be the square of this, so it's going to come with a minus sign because of the I. K squared x0 to the 4th over 4th, right? So this is equal to that. So I don't want this term. Okay, so I need to subtract it. Minus, okay, so 2 of the x0s cancel. K squared x0 squared over 4 dx. Okay, so this is now still a Gaussian integral. You can think of it as a shifted Gaussian integral, although it has been shifted by a complex amount. Okay, but even if that's so, you can just transform variables and carry out the integral more carefully. It really doesn't matter. So this term here doesn't have an effect. The dominating term here is the first term, x over x0 squared. So what we have done is we have shifted the Gaussian, which was originally at x equal to 0, to some other value, okay? But it's still Gaussian. So the area under it is still the same, okay? You can worry a little bit because this is imaginary, etc., but don't worry about it. If you do the integral carefully, it doesn't really matter. So this term here is a constant, right? It's e to the minus k squared. So, excuse me, I can just remove it outside the integral. So I'll end up with a over square root of 2 pi e to the minus k squared x0 squared over 4, and this integral Okay, so that integral just gives me square root of pi divided by the coefficient, which is 1 over x0 squared. Yes?
So, do I have a question? I think I k x0 squared times x needs to be close to
No. Why? The cross term will give an x already. Okay, over here, yes. Okay? Okay, thank you. All right, so let's just calculate what this is. I am going to get A, let's put this in. So A is 2 over pi 1/4, 1 over root x0, 1 over square root of 2 pi, square root of pi times x0 actually. Okay, so let's do some cancellations. So these pi's and the square roots are going to cancel.
Also x0 and square root of x0 cancel.
No, because it's not square root, okay? So, but the 2's will sort of, okay, so this is going to be, please check my algebra, 1 over 2 pi 1/4, right? Because square root of 2 pi will enter here as 2 squared. And pi is there, and I'm left with a square root of x0. Okay, obviously I should also have the e to the minus, okay, e to the minus k squared x0 squared over 4. So e to the minus k squared x0 squared over 4. All right, so maybe we should call this some other constant, so let's call it b. All right, what do we have here? We have our wave function. It's in fact plot wave function squared. So if I plot magnitude of psi squared, which is just going to be the magnitude squared of this, right? Which is going to be the probability density. So it's going to be a Gaussian. Its magnitude is going to be a squared. My a is real. Again, a measure of its width is if I look at what value this becomes a squared times e to the minus 1. It is the place where the exponential, the top of the exponential becomes 1 when I have the square of this. So I am interested in the case when 2x over x0 is equal to squared is equal to 1, which means that x is going to be what? That's not the way, okay? Square. Okay, maybe I shouldn't rush this. Let's just write down what this is. This is going to be a squared e to the minus 2x squared over x0 squared. So what value of x will make the argument of the exponential equal to 1? It's square root of 2 times 1 over square root of 2 x0, right? Please check my algebra. So x0 over square root of 2 and minus x0 over square root of 2, right? So that's some measure of the width of this wave function. Okay, it depends on x0, the way it scales x, and that's what I have. Okay, what about the g of k, the coefficients, or we started calling it the momentum space wave function last time. So this g squared is now going to be b squared. Okay, so my b is real. And I'm going to get e to the minus k squared x0 squared over 2, right? Now this is a function of k. So this 2 is a Gaussian. It looks something like this. Okay, so this is a special case. This only works for Gaussian. When you find this momentum space wave function, you get the same form. You have your homework in which you are doing this on some other functions, and you are getting, obviously, different results. Okay, so again, this maximum here is when k is equal to 0, and it's equal to b squared. So to determine how wide this is, let me again look at the point where this is b squared times e to the minus 1. And that will be when k is equal to square root of 2x0, right? So this is when k is equal to, well, square root of 2 over x0 minus square root of 2 over x0. All right, so what you see now is that the width of one function in coordinate space with respect to x is proportional to x0, but the width in this k space with respect to the k variable is proportional to 1 over x0. So we calculated, for example, various things here. In this case, average value of x turns out to be 0, but the interesting quantity was average value of x squared. You remember what this was?
x0 squared over 4.
Yes, it was x0 squared over 4. Okay, so in fact, you can see that it's just the square of this number divided by 2. Okay, so over here we can just do the algebra, but just from symmetry of the functions. So average value of k squared is going to be the square of this function divided by 2. So it's going to be 1 over x0 squared. Okay, so if you are interested in the momentum squared deviation, that's going to be p squared, which is going to be h bar squared k squared on the average, and that's going to be h bar squared over x0 squared. So the fluctuation in k is proportional to 1 over x0 squared. Fluctuation in x is proportional to x0 squared. So that tells us, okay, so for this problem, delta x was equal to x0 over 2, and delta p was equal to h bar over x0. So if I just multiply them together, I get delta x, delta p is equal to h bar over 2. Okay, so remember we talked this as a limiting case. Any questions? Yes.
Can you give some intuition about why for the Gaussian we see the same shape?
Okay, Gaussian is a special shape that comes out in statistics, in classical statistics. It's a limit of a probability density when you have a large number of variables and you are adding them up. Okay, so
the way Gauss came up with it, by the way, it's all the same Gauss. The Gauss law of electromagnetism, this Gauss addition formula, etc. So all of these things are the same Gauss. And at the time of Gauss, it was important to measure various quantities very precisely, especially they are trying to measure positions of stars very precisely. And they noticed that no matter how much they increased their precision with the technology that they had, the position of a star had some brightness which looked like that. So you don't know where the exact position of the star is, but it's diffuse, etc. And Gauss tried to engineer his way out of this. So he said, okay, what are the things that are causing this uncertainty? Well, maybe the telescope is vibrating, maybe, this atmosphere is doing this and that, etc. So there are lots of random events, each of them with their own probability densities. But if you add them all up, that always approaches this special form, this special shape. It's Gaussian. It's called the central limit theorem in statistics, but it's just for classical statistics. So, but this thing crops up all over the place, also in quantum mechanics as well.
Okay, but I especially meant why the Fourier transform appears in the same form.
Why? I don't have a good answer for that. I guess if you wanted to solve a problem like that, find the density whose Fourier transform is equal to itself, you might end up with the Gaussian, But offhand, I wouldn't be able to provide you with the algebra here. Good exercise for you. Try it. Other questions? Okay. So, where are we? Let's look at a few other properties associated with it. One thing we can look at is we can check the normalization. One of the problems in Griffiths is to prove this in general for any psi, that when you find this G, if psi is normalized, G is normalized also. So that's again good exercise, but let's just verify this. Let's just verify whether this G of k, dk minus infinity to infinity, is it still equal to 1, whether the normalization is conserved. So what do I have? I have this b. So this is going to be b squared times e to the minus k squared x0 squared over 2, because the original g function is 1 over 4. So if I square it, I get 1 over 2 times dk. Minus infinity to infinity. So that's actually, again, the same integral. So I'm going to get square root of pi divided by this coefficient, which is x0 squared over 2. So I'm going to end up with square root of 2 pi 1 over x0 times b squared. So let's put in what b squared is. So b squared is 1 over square root of 2 pi, times x0. And indeed, I have square root of 2 pi 1 over x0, which is equal to 1. So very nice. The normalization is conserved. Obviously, this should be true for any function, otherwise it's not very useful. What else? Let's just see what happens when I shift this Gaussian in one space or the other. Okay, so suppose if I'm given this psi of x0 is equal to e to the minus x over x0 squared plus I k0x. So we now know what this does. It gives momentum to the particle. It gives a momentum of h bar times k0. So let's see what's going to happen. Obviously, there's still the normalization, A. So what happens when I try to find G? So G of K is going to be equal to e to the A times, okay, let's see, e to the minus x over x0 squared plus I k0 x, okay? And then I'm going to get e to the minus I kx dx integral and a 1 over square root of 2 pi because of the transformation. All right, and what will that give me? A over square root of 2 pi e to the minus x over x0 squared. And let me write this as plus I k0 minus k x dx. But this is actually the same integral that I have here. Okay, so I have the same integral in the bottom here. The only difference is, yeah, well, instead of k there, I now have, okay, in fact, let me put it in the same form. Let me make this a minus and make this a k minus k0 so that it's I minus something times x as I have over there. And I got that g of k. And at the end, I got this expression. So I can easily determine what this is without going through that algebra. Instead of using k, as in the previous equation, now I'm going to use k minus k0 because that's just a constant, okay, which doesn't enter into the integration. And the end result is going to be then b e to the minus k minus k0 squared, okay, and x0 squared over 4. So it's just like the previous, okay, derivation. You can just go through the same steps again, except that in place of k, you are going to get k minus k0. So what does that mean? That means now I obtained a g of k, which is centered around k0 instead of 0. So I'm going to now get average value of k equal to k0, or multiplying through by h bar, average value of p, which is going to be average value of h bar k, will be h bar k0. Okay, but this is something, again, we worked out earlier when we were looking at this function and we found what p and average value of p and average value of p squared was, etc. Okay? So we are just regenerating all of this stuff. Any questions? Okay, finally, let's also shift this in the on the x-axis. All right, so it's this time take psi x0 to be equal to a again, e to the x minus some distance a squared over x0 squared. So again, I have my Gaussian, except that this time my particle is expected to be found at which location? Okay, at x equal to a, because now this is what my psi looks like. Okay, so it's yes, I forgot the minus sign, otherwise I'll have a disaster, right? It's not going to be normalizable. Yes.
Are you gonna take that out? Are you gonna take that out?
Yes, good idea. Thank you. Okay, we'll start with you. Okay. Let's see. So what do we do now? How do we find our g of k? So g of k is going to be a over square root of 2 pi, an integral of e to the minus x minus a squared over x0 squared, and minus I k x dx, minus infinity to infinity. Okay, so again, by just playing around with variables, we can transform this to an integral that we already evaluated. And the way to do it is to take this factor here, x minus a, and call it something like u, okay? And so I'm going to put x minus a is equal to u, which means dx is going to be equal to du. And x is going to be equal to u plus a. So this is going to be a over square root of 2 pi, integral minus infinity to infinity, e to the minus u over x0 squared. So it's the same integral really. And then I have minus I k in place of x. Now I have u plus a du. Okay, but this factor here, e to the minus I k a, is a constant. Okay, there's no u dependence in it. So let me factor that out. I'm going to get e to the minus I k a, all right, a over square root of 2 pi, minus infinity to infinity, e to the minus u over x0 squared minus I k u du. But this is our previous integral. Okay, the dummy integration variable has been changed from x to u, but as a function of k, this is exactly the same thing. So I can just put in that term. So it's going to be e to the minus I k a, okay, b times e to the minus k squared x0 squared over 4. All right, so what does this say? This says, okay, that there's this dualism between the momentum and coordinate spaces. If you shift the wave function in the coordinate space, if you take the particle from origin to A, its momentum distribution doesn't change apart from this phase factor. Okay, so it is important. So although it's a phase, by adding this phase to the momentum, the equivalent wave function in coordinate space shifts in space. Similarly, we discussed this before when we discussed this e to the I k0 x term, this term here, that if you are going to get a shift in the momentum, that corresponds to a phase term in the coordinate space. Okay? So there is this nice duality. So the coordinate variable is not very different from the momentum variable in terms of the algebras that we are carrying out. Okay, so we have a momentum space wave function, which is the g. We have the coordinate space wave function, which is the x, the psi, and we can find averages with respect to one or the other. Now, the reason we started out this was to find how psi was changing as a function of time, right? So when psi is changing, let's continue someplace. We're doing on time, okay. So here I'll leave the integral there. Okay, so again, suppose we have this psi x0 equal to a e to the minus x over x0 squared. We know that we can express this as a sum of eigenstates of the Hamiltonian, which in this case are in this form e to the I kx's, e to the I kx dk. Okay? And this g of k is something we know. It's the expansion coefficient. Okay, we determined it's approximately 3 times during this hour. But what happens when I am interested in the time dependence? Well, each term now is going to be multiplied by this e to the minus I energy time over h bar term. Okay, so it's going to be 1 over root 2 pi minus infinity to infinity g of k e to the I kx, but now also and minus I e of k, okay, however, I have to put in the energy dependence as a function of k, t over h bar dk. So let's put everything in. Okay, so now this is going to be b over square root of 2 pi. G of k is e to the minus k squared x0 squared over 4. Let me put in the energy term next because that's also quadratic in k. Okay, because E of k, remember, is h bar squared k squared over 2m. That's how energy depends on k. Okay, so one factor of h bar cancels, and I have minus I h bar squared k squared over 2m times t plus I kx dk minus infinity to infinity. All right, looks like a difficult integral. It really isn't. Why? Because it's still Gaussian. Okay. So, in fact, let me just write. I'm not going to evaluate the integral, but just discuss what you get out of it qualitatively. Okay, minus infinity to infinity, e to the, okay, something times k squared. So minus x0 to the 4 over 4 plus, there's one less h bar here, right? Because h bar cancels. H bar over h bar t over 2m, and then I. Okay, all of this thing times k squared plus I k x dk. So again, whenever you get these Gaussian integrals, the thing that you need to do is just look at the coefficient here and k and kx term, etc., and try to get a term which is the, we say, square with respect to k plus something. Yes?
What about x0 over 4?
X0 to, I'm sorry, x0 squared, right? Sorry about that. Okay, please check my algebra. Thank you. Okay. So this term there, now I can again attempt to write as a nice square. So I can just try to write this thing as x0. In fact, let me give that a name because I don't want to carry that all along. Okay, let's just give that name. Okay, let's call it alpha because it's going to look like that. Okay, so let me call this bit equal to alpha. So if I write that term as e to the minus alpha k plus, so minus I x over 2 alpha
We have k squared, not k.
hmm?
So minus alpha times k squared.
Okay, let's see. Minus alpha, yes. So let me call that. Okay, I don't want the alpha. No, I think I'm okay. Right? All of this thing squared. Okay? I'm going to get this term, which is okay. I'm going to get that term, which is okay. But I'm also going to get an extra term, which is not okay. So I want to subtract that out. Okay, so that's going to be minus, because of the square, another minus, so it's going to be plus. So to correct it, I have to put in a minus x squared over 2 alpha, 4 alpha.
Squared.
No,
Squared. Alpha squared.
no. 1 factor of alpha cancels, okay? So that's equal to that. Integrated minus infinity to infinity dk. So again, this factor is just a constant and will come out of the integral. And the rest of the integral is going to be, okay, a Gaussian integral whose result we know. So I can even squeeze the result here. It's going to be, so let me keep the b over root 2 pi here. So it's going to be b over square root of 2 pi, and then square root of pi over alpha, where alpha is that alpha. And I have e to the minus x squared over 4 alpha, okay? I told you I was not going to evaluate the integral, but it was so fun, I couldn't stop myself. So in any case, qualitatively, if you look at what's going on, alpha has time in it. So the magnitude of alpha is increasing. That means that the Gaussian is spreading, okay? So if I just look at this Gaussian as a function of time, here we have not given it any momentum. But if this is what's the Gaussian is at t equal to 0, you see the alpha is here in the denominator also. So its magnitude is decreasing. And it's also scaling x squared. So the Gaussian is spreading. So at a later time, I'm going to get something like this. At a later time, I'm going to get something like that. You can check that it's always normalized. It has to be to obey the Schrödinger equation. Okay, so it's just spreading out. The uncertainty in x is increasing systematically. Okay, since this is a complex quantity, you have to be careful in obtaining psi star psi and looking at what the curve looks like, but qualitatively, this is what the Gaussian is doing. If it had some initial momentum, if I just add in a term here, I k0x, that it has momentum, the only thing that will change is that, okay, this Gaussian at time equal to 0 will be there. The next time period is going to be somewhere over here. Later on, it's going to be there. Okay, so it's going to spread and, okay, propagate in the x direction. All right. Oh, okay, let's stop. I'll see you Thursday, yes.